Your training job doesn't die because math is slow. It dies because memory runs out and the system starts thrashing. The stake is clear. Either you buy more boxes or you find a way to get more RAM than fits on a board without torching bandwidth and latency. Compute Express Link, or CXL, is a standard that lets processors and accelerators access outside memory devices with cache-aware connections over a high-speed link. In plain terms, it stretches your memory space beyond the sockets on your motherboard while still behaving like memory, not like a disk. Pooling means many hosts draw chunks from a common memory tank, but each chunk is owned by one host at a time. Sharing means multiple devices can touch the same memory region at once with rules that keep data consistent. Here is the simple idea. Keep your local DRAM for the hot working set, then extend the cold or bursty part of your footprint into pooled memory boxes linked by CXL. Coherence is the glue that makes this feel normal to software. When a core or an accelerator writes a cache line, a home agent keeps track so readers see the new value, which avoids the two versions of truth problem. Switching is how you scale beyond one cable. Devices and hosts connect to a CXL switch in a star or small fabric, and larger deployments stitch multiple switches into a tiered topology so many nodes can tap the same pool. These links behave a lot like onboard PCIe lanes, but with memory semantics layered on top. That means reads and writes complete in far fewer steps than storage I/O, which keeps the programming model simple. Think of it like NUMA, where some memory is local and some is remote. Allocators try to keep hot pages local and push cooler pages into the pool, and schedulers steer threads toward the memory they touch. Now the cause and effect that matters for users. When a job exceeds local DRAM and spills to storage, tail latency explodes. With CXL, those spills are handled by pooled DRAM at microsecond scale, so the worst requests shrink and jitter drops. A useful back-of-the-envelope is this. Local DRAM is roughly a tenth of a microsecond, pooled CXL memory is about 1 microsecond, and fast SSDs are tens of microseconds. That single tiering jump from disks to pooled DRAM can save an entire class of timeouts. Bandwidth and compute must still balance. A single CXL link offers far less throughput than a package full of stacked memory, which means you should park your hottest tensors on local DRAM or HBM and send the long tail to the pool. Cache hierarchy is your friend when tuned to this layout. Large last-level caches absorb bursts, prefetches soften small strides, and background movers drain cold pages to the pool before they clog the fast path. Context length makes or breaks the decision. As sequences get longer and key value buffers swell, the working set inflates unevenly, which is why a pool that expands on demand keeps tokens per second steady instead of falling off a cliff. Thermal and power delivery live mostly inside the boxes at the ends of the links. The PHY that drives each CXL lane costs a handful of watts, and the pooled chassis has its own budget, which you trade for higher utilization across your fleet. Packaging limits show up less on the board and more in the topology. You can only hang so many devices behind a switch before oversubscription creates head-of-line blocking, so planners carve pools with ratios that match real workloads. Coherency overhead is the first bottleneck to respect. Keeping caches in line across devices burns bandwidth and adds control traffic, which means careless sharing patterns can erase the benefit of pooled capacity. Topology hops are the second trap. Every switch adds nanoseconds and a small risk of congestion, which is fine for bulk reads but painful for chatty, random access. Quality of service decides whether neighbors hurt each other. Without per-tenant limits and priority lanes, one job can flood the fabric and inflate another job's tail, so operators set caps and reserve lanes for latency-critical flows. Why this matters is simple economics. Instead of over-provisioning each server for the worst day of the year, you right-size local memory and burst into the pool when models or contexts spike. Training gains because crashes from out-of-memory errors vanish, and batch sizes can grow when there's headroom. Inference gains because rare big requests avoid paging to storage, which keeps the slowest responses closer to target. Energy follows the same logic. Pooled DRAM costs more joules per byte than on-socket memory, but it costs far fewer than bouncing through a storage stack, which means fewer watts per useful token when the pool prevents thrash. Reliability looks different but improves with the right controls. If a pooled device fails, the job can remap pages to another device. If a local DIMM fails in a standalone box, the whole node might drop. Cost maps back to the wafer the same way it does for compute. By decoupling memory growth from host chassis, you sweat assets longer and raise overall utilization, which lowers cost per served request even when the pool carries a premium. There are clear trade-offs. If your model is bandwidth-starved rather than capacity-starved, a CXL pool does not feed the math units like wide on-package memory, so utilization might still sag. If your access pattern is tiny, random, and latency-sensitive, remote hops can hurt more than they help. In those cases, you keep the hot set and the locks local, or redesign the data layout so remote reads are chunky and predictable. Early fabrics are straightforward and conservative. One switch, a few hosts, a handful of memory devices, and basic policies that keep temp data local while the pool catches overflow. Maturation brings multi-switch topologies, fabric managers, and richer scheduling. Allocators learn to place pages by heat and lifetime, and queues harden so tenants cannot starve each other. Security and isolation get stronger too. Keys, encrypted links, and device attestation allow pooled memory to behave like a private extension of each host SRAM instead of a shared attic. Device diversity expands the menu. You will see standard DRAM pools, near memory caches that sit closer to accelerators, and tiered pools that blend cheaper, slower media for bulk datasets that rarely move. Operating systems and runtimes are catching up. Hints from compilers and frameworks can tag buffers by hotness, so allocation across tiers matches the way the model really runs, not just how the programmer guessed. Finally, you have to compare this to buying more stacked memory on the package. HBM gives you thousands of gigabytes per second right next to the compute, but only so many gigabytes, while CXL gives you many more gigabytes with far less bandwidth. The decision rule is crisp. Choose CXL when capacity limits break jobs, when swapping or out-of-memory resets dominate, and when you can tolerate about a microsecond class hop for cold pages. Choose more HBM when bandwidth is the wall, when math units idle waiting for data, and when the working set actually fits if you feed it fast. Many fleets will do both, HBM for the fire hose and CXL for the lake. Keep two principles in your pocket. First, place hot data where the wires are shortest and the lanes are widest. Second, use pooled memory to prevent rare spikes from sinking throughput for everyone. Subscribe for more Future Forge.